So thank you very much for the kind invitation, for the possibility of being here. So, okay, maybe can you see or no, maybe? Yeah, right, but just afterward. So maybe at the beginning it will be on slides, see, and then yes, at some point. No, thank you, but at some point that will be helpful because I mean, as promised in the in the title, there will be some bunch of formula, some bunch of concept for the mass that will be proposed, and one of the aim of this talk is to show how those concepts are in some sense naturals and they interact with each other. Okay, and okay. So before starting, let me mention the collaborator. Together with I'm running this project. So Virginia Agostiniani from Trento, Luca Benatti that is now in Pisa, Stefano Borghini who is in Trento, Mattia Fogagnolo in Padova, Carlo Mantegazza in Naples, and Francesco Ronzio in Rome. Okay, so let me start. So essentially, yeah, some of this idea, I mean, some of that are very classical. Okay, some of the concepts maybe are, yeah, like the ADM mass are, I think, known to everybody in the audience. Some other concepts are more recent, and some of them are kind of new. And actually, we introduced them after we get some results, some speculation, in which we managed to use a very simple tool like a potential theory in order to deduce geometric inequalities and eventually also inequality involving mass. So let me start just to give you an idea of what the tools are, which, I mean, as I said, they're very simple. Let me start with the simplest possible situation. So we consider an harmonic function, okay? So solving the exterior Dirichlet problem in the exterior domain, okay? So suppose we are in a complete non-compact manifold M3. Suppose we have a bounded domain with smooth boundary, omega. Okay, let us consider let's say the capacitor potential, right? And for the first slides, you can even imagine to be in R3, right? So because some of the formula were new already even in Euclidean space. So you pick the capacitor potential of U, okay? If omega is a ball, everything is really elementary. You really have the green function. Everything is rotationally symmetric. Okay, and what you can introduce is this function. So you have this f of tau. A priori, it's not clear why it should be interesting. So essentially, you integrate the gradient over the level set of your potential, and you rescale by tau square. And yeah, first observation is that if omega is really a ball in R3 and everything is rotationally symmetric, this quantity is constant. It doesn't depend on tau, so it's constant along the level sets. Right? When you compute it on each level set, you always get the same value, right? Because essentially because the green part is constant. By an explicit computation, and also this weighted volume is also constant. The weighted volume is also constant. So the first observation is if everything is rotation symmetric, F is constant. More interestingly is that in general, it is not constant, but it is monotone, right? So you pick any domain, you build the same quantity here, and what you get is the derivative as a sign, the derivative of f, of capital F as a sign, okay? And moreover, this monotonicity can be used to detect the geometry of the domain in the sense that the monotonicity is strict unless omega is a ball. So you can characterize ball, for example, looking at if you have a strict sign or not there. Okay, that was new even as I said in Euclidean space. And here is a sketch of the proof, but I don't want to enter into detail because here's just smooth computation. So I'm sorry, because here's for those smooth Lorentzian geometry, here I'm doing smooth Riemannian computation. No one would be offended by this. Okay. Okay. So essentially, you take two derivatives. I mean, just to have an idea of how thing works. So you take two derivatives, and you realize that you have a sign here. And essentially, here I put, even though I said that we are in Euclidean space, I put the Ricci nu. So if you are Euclidean, you are 0. If you have non-negative Ricci, this is still okay because you have a sign for the second derivative. And then you get the monotonicity just integrating, because you realize that by the asymptotic behavior, you realize that the first derivative of tau goes to 0 for large tau. And also, in what I'm saying in a few minutes, so beside the case of non-negative manifold with non-negative Ricci, you may also consider weaker curvature condition, like the one which are natural when you consider initial data, asymptotically flat initial data in GR. So in this case, you are led to consider a manifold with non-negative scalar curvature. In this case, you can also find some refinement of this formula in which you substitute the Ricci nu term by means of the Gauss equation, right? So in case your curvature assumption is weaker, you are not completely lost. You can go farther. Okay, I forgot to say that here the computation that I made here are three-dimensional, but essentially the Euclidean and non-negative Ricci part, they extend also to all dimension. Whereas for the scalar curvature, we need to use at some point Gauss-Bonnet. So for the scalar curvature, we need to be three-dimensional. And for the sake of comparison, I decided to use all the formula in 3D, right? So here, what I said before, so from the sign of the second derivative, you just integrate and you realize that the f prime of tau is going to 0 for large tau, and so in the end you get the monotonicity. So the monotonicity is nice because, okay, it's strict unless you are on a ball, but you can use it, you can exploit it even in a geometric way. So here the idea is, as I said, is to look at, you have a static situation, right? Because you have a harmonic function solution to an elliptic equation, but you consider, you want to consider the level set as a kind of evolution, right? The level set flow. Here's the idea. So essentially you can compare, now that you know that the function is monotone, you can compare the value on the boundary with the value at infinity, right? And so if you do that, at infinity you can take advantage of somehow of the nice behavior of the function, which, I mean, in Rn is clear because no matter what the domain you start with, no matter what is the geometry of the starting domain, the solution is always asymptotically rotationally symmetric. But even on manifold with non-negative Ricci, you can compute the value of the limit of f of tau, and actually what shows up is this correction with respect to the Euclidean quantity, which will be just 4 pi. And in general, you take 4 pi times the asymptotic volume ratio of the manifold. Okay? And what you have in one is just grad u square, but you use again the fact that the first derivative as a sign, and you combine this with the Holder inequality to see that this one is controlled by h square over 4. So putting all these things together, what you get is the proof of that we obtained together with Virginia and Mattia, okay, of the Wilmore inequality holding in manifold with non-negative Ricci, okay. And again, you may also characterize the equality case, okay. In fact, if you have equality, okay, in Euclidean space, you know that omega is a ball, okay. In general, when you have non-negative Ricci, what you have is this kind of rigidity statement, saying that the exterior, I mean, inside omega, you cannot say anything, but outside, if the equality is achieved, you are on a truncated cone, right? So there is a very strong characterization of the equality case. It's sharp and the equality is characterized. Okay. So let me come back, and now I want to introduce, not all at the same time, but I want to start introducing some concept of mass. So to do that, I take advantage of this inequality, okay, the Willmore inequality. For example, consider the case with where the asymptotic volume ratio is 0, because in the end we are going to consider the case of asymptotically flat initial data. So asymptotically flat means that you are at infinity you are approaching Euclidean space. Euclidean space has AVR equal to 1. So for what concerns the implication on mass concept, AVR equal to 1 would be great. And so in this case, we get the classical Willmore inequality. So 16 pi is the lower bound of the integral of h square. Okay, and so we can consider a related quantity, which is the deficit. So we can consider the difference essentially between the left-hand side and the right-hand side. Okay, we write in this fancy way. So this is a sort of Willmore deficit. And if you normalize it, okay, by this quantity in order to make it scaling invariant, what you get is the so-called Hawking mass, okay? And, and this is the first concept of, this is another classical concept, okay? And I wrote it down here, okay? Okay, just for the sake of reference in the next part of the talk. So most of these concepts, I mean, this concept of mass are always built. I mean, this is sort of a archetypical way of building a concept of mass in which, in a sense, you're going to measure the deviation from being Euclidean. Okay, so okay, so that's the point. If you use an exhaustion, so this is a quasi-local concept of mass, meaning that essentially that was introduced by Hawking in the attempt of aiming at describing the quantity of mass which is enclosed by the boundary of omega, right? And of course, if you you consider an exhaustion, so when the boundary, when omega is exhausting all your manifold, you get a concept of total Hawking mass, okay? And you take the limb soup and you take the supreme over all the exhaustion, okay? And you build a global concept of Hawking mass, okay? So no, this is just a remark. And then, yeah, in 3D, you can use actually, you can use the Willmore inequality that you already established also to deduce the isoperimetric inequality. In Euclidean space, I mean, that's not the way to deduce the isoperimetric inequality, but for example, in negative Ricci curvature, I mean, you can also adopt this strategy, and this inequality was how to say, inspired by some idea of Wisken, in which he combines the mean curvature flow together with the validity of the Willmore inequality to deduce this kind of isoperimetric inequality. And soon afterward, this was generalized to every dimension by Brendel, and then even exported to non-smooth setting by Balog and Cristallini. And as soon as you have this inequality, which is sharp in this case, you have a very sharp characterization, meaning that the equality is achieved if and only if your three-dimensional manifold is isometric to R3, okay? And you can exploit this quantity in the same way that we just made with the Willmore inequality. Okay, here was the idea of the proof. Sorry, yeah. Yeah, right. Sorry, I forgot R3. Yeah, this is a GR3. Sorry. Thank you. Yeah, is the Euclidean one. And here we play the same game actually. So in the case in the case where the AVR is 1, okay, you have the classical isoperimetric inequality. You can consider the isoperimetric deficit suitably normalized in order to make it scaling invariant. And what you get is a quasi-local, so-called quasi-local isoperimetric mass. And then you can construct the global quantity, taking the lim sup, and then taking the sup over all the possible exhaustion. Okay, and this concept was introduced by Wisken in 2010. And okay, one advantage of this, actually, as we're going to see the interplay as far as we can, as far as time allows, the interplay between these various concepts and the classical one, which was the concept of mass introduced by Arno Wideser-Miser in 1961. This is the ADM mass, okay, and it's a priori is a coordinate-dependent expression, okay, which is actually it was shown by sorry, misspelled, Bartnik and Krushel in 1986 that there are sharp condition, okay, sharp decay condition under which this number here is a geometric invariant, so that the definition does not depend on the particular coordinate system. In particular, you need that the metric tends to the Euclidean one, okay, together with its first derivative at some rate. So, so here you have a weight mod x to the power tau, and tau should be larger than 1/2. So it is nowadays well known that these are the sharp assumption in order to have a well-defined ADM mass. So a first advantage, which is how to say very evident, is that, for example, isoperimetric mass is less. I mean, if you want to define the isoperimetric mass, it's you don't have to introduce asymptotically flat coordinates. You don't have to ask decay of your metric towards the Euclidean one. Okay, so in general, you just need to compute area and volume and take the difference. So it's in general, this concept makes sense even in a broader class of manifold. Okay. And also for the Hawking mass, even though, I mean, in this case, it's a little bit more sophisticated because you need to compute the integral of h squared. So, I mean, it's a little bit more sophisticated, right? But this isoperimetric mass, it's very general. And so, I mean, a natural question is the following. I mean, it's very natural. So, you know that the ADM mass well, there are essentially two theorems that maybe I'm going to mention here, okay, for the ADM mass, which are very fundamental result in the Riemannian geometry, but also in the mathematical study of general relativity, which are the positive mass theorem and the Riemannian Penrose inequality. So, I mean, a natural question would be try to see whether this theorem holds true also for this other concept of mass. Okay, so eventually in a broader class of manifolds. Okay, so that's the problem that we try to answer. So here I just recall the setting. So now our curvature assumption is non-negative scalar curvature, which can be interpreted as an assumption about non-negative mass, non-negative energy density. Okay, and yeah, here's the definition. Cm tau asymptotically flat means that you have m derivative and they decay this power, okay? And if you derive them, then they decay for the first derivative, the difference between the first derivative decays to the same power minus 1, two derivatives x minus tau minus 2, and so on. Okay, so this is the shorthand notation to see that. You have those decay. As I said before, I mean, by this result, of Barton and Cruchel. These are two different papers, so the two independent results. You have that the mass is well defined whenever you have this first order decay to a rate which is at least 1/2. Okay. Moreover, I mean, this is for having a well-defined object. Moreover, you also have this other fact. You have that okay, being well defined a priori would mean also to be plus infinity, right? But you have that as soon as the scalar curvature is in L1, then you also get a finite number, which is fine because I mean, if we believe that Rg should represent some sense the energy density, I mean, the first attempt would be to integrate the energy density to get the positivity of the total mass, which, I mean, doesn't make any sense. But at least whenever the energy density can be integrated giving a finite number, the total mass is a finite number as well. Okay. So as I said, the fundamental statement for this concept of mass related to the ideal mass are the positive mass theorem, say that if I have an asymptotically flat manifold with non-negative scalar curvature, then mass is non-negative, and the equality holds if and only if you are isometric to R3. So you see, it's again an inequality, sharp inequality with a very strong rigidity statements. And let me mention the fact that in the original paper, but also in the following refinement or new proof of the same statement, I mean, the decay assumption, when you say asymptotically flat, the decay, you should make precise, okay, you should in principle specify what M and tau are, okay? And so in the general statement, I mean, the assumptions are far from being optimal, far from being the one which are which I wrote there, okay? And also, I mean, but concerning the positive mass, actually, we realized that there was a quite richest paper by Le Floch and Lee, in which they managed to prove positive mass under optimal decay assumption. So under this, the assumption that are needed in order to have a well-defined ADM mass. And then there is another very nice theorem concerning the constant of mass, which is the Penrose inequality, okay? And this was proved in 2001 by Wiskin and Mannen in the case of one single horizon, and by Bray still in 2001, the more general case in which you are allowed to have several horizons. Okay, so in this case you have a Riemannian manifold with non-negative Ricci, but now you have a boundary which is non-empty, but it has some property. It is an outermost minimal surface, meaning that the H is 0, and essentially they are not is not encompassed by other minimal surface. There are not other minimal surface around him, dividing him from the infinity, essentially. So if this is the case, okay, then you have this state, you have the validity of this inequality that can be seen as an enhanced version of the positive mass theorem. So the mass is not only positive, but it is at least as large as the square root of the area of the boundary divided by 16 pi. Okay, so so essentially. And the equality, you have also a rigidity statement that I forgot to mention here. The equality is achieved if and only if you are on a Schwarzschild manifold. You know, a space-like slice of the Schwarzschild manifold. Essentially, you have that as soon as you have an horizon in this situation, okay, the mass is at least the mass of the space-like Schwarzschild manifold whose horizon has the same area of your initial data, okay? And again, so the asymptotically flat condition here are still the non-sharp one, okay? So that was open problem. So is it possible to prove the Riemannian Penrose inequality under the least possible assumption that allows to have a well-defined ADM mass? So this is another question. Okay, so let me, so what? Sorry? I mean, we put we already put a preprint on the archive, so it's about okay. No, it's just to to let the people being interested in what's coming next. But actually, we managed to prove the Riemannian Penrose inequality under the optimal assumption. And sorry, how much time? Okay. Okay, let me try to. So again, you have a monotonicity formula. Okay, let me explain. Okay, the approach here. Okay, so essentially. The same idea based on the monotonicity formula along level set of harmonic function revealed to be successful even in this situation. Actually, we have a paper together with Virginia and Francesca Oronzio in 2021, in which we managed to find the suitable quantity, okay, that is now monotone along the level set of a green function, okay, built on this asymptotically flat manifold with no negative scalar curvature. So we managed to prove monotonicity formula, and then we exploit in the same way, okay, so you compare what you have at the origin to what you have at plus infinity, forget about this corollary, but essentially what you have is that you can prove essentially positive mass theorem using green function. And okay, here's the idea, but okay, let me skip. An interesting byproduct of the proof is that actually you can use the monotonicity to characterize a non-negative scalar curvature on those manifolds using small sphere limit. Okay, so essentially here, just look at the statement here. Okay, so you have that the scalar curvature on element3 is non-negative if and only if the quantity that you can build with a green function with pole at Q, okay, is monotone. So you are on a asymptotically flat manifold. You pick a pole Q. You consider the green function with pole at Q. You build your quantity, okay, and the quantity is monotone, okay, if and only if the scalar curvature is non-negative. So if you are monotone at each point, okay, so around each point, then you can use it to characterize the negativity of the scalar curvature. Okay. Okay. So far, this is a potential theoretic approach toward the positive mass theorem, but you can also draw a nonlinear potential theoretic approach toward the Riemannian Penrose inequality. In this case, you consider p harmonic function. Again, okay, let me skip the details, but again, you have another monotone quantity, okay, and you play always the same game. You compare what you have at the on the boundary, what you have at plus infinity, and eventually you get the statement that you like. So the Riemannian Penrose inequality. You have to take the limit. I mean, what you get at first sight is an inequality at level of at p level, but then when you let p goes to 1, you recover the clean statement, the clean geometric statement. Okay, and so now I can use some of the things that I wrote on the blackboard. So what's the relationship, okay, between this new proof and the already existing proof? For example, let us focus, for example, in the case of Riemannian Penrose inequality, which was, let us consider, for example, the proof of Wiskin-Mannen, okay? Essentially, in this very nice paper, it's a very seminal paper, I would say, actually, they managed to prove that the Hawking mass is monotone along the inverse mean curvature flow. So this is the smooth computation was known since the 70s. It was due to Grosch. Okay, so what they managed to prove is that this smooth computation can be made rigorous, even in presence of jumps, because in general you don't have a smooth flow. In general, your flow is crazy, can jumps at some moment. So the main contribution of Wiskin-Mannen paper is just to give a rigorous proof of the validity of Grosch monotonicity. Okay, and here essentially we play the same game, but instead of using the weak formulation of the inverse curvature flow, we consider p-harmonic function. The p-harmonic function are related to the inverse curvature flow formally because essentially if you perform this change of variables, so if up is a p-harmonic, then you can build up this wp, and the wp satisfies this equation here, which looks not very nice. But when p is going to 1, what you get is that the p Laplace becomes the 1 Laplacian, and grad wp to the p is just the length of the gradient. But the 1 Laplacian is the divergence of the normal, so it is the mean curvature. So essentially, when p goes to 1, what you get is the level set formulation of the inverse mean curvature flow. Okay, so essentially, but the advantage is that here, in general, the solution is just Lipschitz, whereas there, you know that is C1 beta. Okay, it matters. I mean, when you have to justify the computation also in presence of possible jumps, it helps a lot. Okay, even more regularity. That's why the proofs are simple than the original one, and can be explained also to master students. Actually, what we have here, the theorem that we have together with Virginia, Carlo Mantegazza, and Francesco Ronzio, is that we managed to prove that the quantity that I wrote before is monotone along the level set of this p-harmonic approximation, let's say, of the inverse mean curvature flow. And the quantity can be rewritten in this way, I mean, in this equivalent way. So this is the first row. Okay, so in the first row, we wrote this quantity here, and we managed to prove that this, let's say, p-harmonic version of the Hawking mass is monotone along the level set flow of the p-harmonic function. And when p goes to 1, the quantity also formally tends to the Hawking mass. Okay, so essentially we have all the picture is completed also at the p level. So we have this p concept, the nonlinear, the p-harmonic concept of mass, let's say, that eventually recovers the Hawking mass when p goes to 1. Okay, and okay, and okay, so so what about the isoperimetric mass? Okay, so the fact is that also for the isoperimetric mass, you can build essentially a p version, a nonlinear version, essentially, considering the deficit. Essentially, this is the normalized deficit in the isocapacitor inequality. Okay, so for p equal to 2, there was this concept introduced by Jargui and Lee, but you can also build the same concept also for generic p between 1 and 2. And when p goes to 1, the p capacity goes to the area. And so also for the isoperimetric mass introduced by Wisken, you have a p version of that. Okay? So once you have the monotonicity of the Hawking mass, you can combine it with an asymptotic comparison lemma, says that essentially the p Hawking mass, let's say, the p version of the Hawking mass, okay, is controlled by the p version of the isoperimetric mass. Okay, and this is the asymptotic comparison lemma, which was at the heart of this result, obtained together with Fogagnolo and Benatti. And as a corollary, okay, you have that by the monotonicity of the p Hawking mass, you compute the p Hawking mass at the origin, you get essentially the p capacity to power 1/2. But then this is less than the p Hawking mass, the limit at infinity, but the limit at infinity can be controlled by the p isocapacitary mass. So when you let p goes to 1, this goes to the area, and this goes to the isoperimetric mass. Okay, and so essentially you get this generalization, this extension of the Riemannian Penrose inequality also for the isoperimetric mass, which means that actually this inequality holds true also even in a large class of manifold. Essentially, as soon as you have a well-defined inverse mean curvature flow, as soon as you have a solution to this one, essentially you have the isoperimetric mass. Yeah. Not any. You're right. It's not asymptotically anything. It's just, I mean, there are class of for example, if you have, you can somehow describe some relevant class of manifold in which you can make sure that you have an inverse mean curvature flow. The existence of an inverse, for example, if you have a C0 asymptotic, for example, you C0 asymptotically flat, that's enough. But I mean, right. Right. No. We don't need, not even the derivative. No, because I mean, for the isoperimetric mass, the advantage is that it's a C0 concept. Like, okay, it's a zero. Right. That's the point. Well, as soon as you have your decay assumption, you get that the concept are all coinciding, even at P level. But I mean, what it's interesting is at that level. But even at P level, as soon as you have asymptotically flat initial data with the proper decay that was prescribed by your theorem, actually you get all the concepts make sense. They coincide with the ADM mass, and so gives you also the improvement of the statement in the sense that you can really state that with the optimal decay assumption you have the validity of the inequality, right? Right, and thank you.